So first of all, we have to do what's left from last time. The first thing is question 15, which asks for the following: the map f from the integers into the integers, sending each x to 1/2 times x squared plus x to the 4th. Is should be shown to be not a polynomial map, but a compatible map. Now, it's not a polynomial map because Z is a torsion-free ring with a torsion-free abelian group, and so we have the correspondence, a 1-1 correspondence between polynomials and polynomial functions, which, on the other hand, allows us to compare coefficients. And so this thing here is really 1/2 times x squared and so on. And so it's not a polynomial with integer coefficients. It cannot be a polynomial with integer coefficients, and hence it's not a polynomial. The next thing is to show that it's compatible. So take an an ideal of Z, and you know every ideal is a principal ideal, so it's generated by some natural number n. And we would like to show that it f preserves the congruence, which means that we have to choose, say, two elements x and y, such that x and y are equivalent with respect to this ideal I, which means that their difference is in I, or that their difference x minus y is a multiple of n. Now this means that they are congruent in this way, and then we have to find out if the images are also equivalent to I. So we have to show that f of x and f of y are also related to I, with respect to I, which means that n is a divisor of the difference. So we have to show that n divides f of x minus f of y. Okay, let's simply split into our hands and start doing this. What is f of x minus f of y? If you plug in here, it's just 1/2 times x squared plus x to the 4th. And then we can simply continue, minus y squared minus y to the 4th. And here you can see that in the second part, well, let's do it in this way, rewrite it as 1/2 times x squared minus y squared plus x to the 4th minus y to the 4th. Now you can see that x to the 4th minus y to the 4th, that's just x squared plus y to the 4th times x squared minus y to the 4th. And so we can subtract x to the squared minus y squared. And what remains here is 1 plus, and if we take this out, it's x squared plus y squared Okay, now we know that n divides x minus y. This is x minus y times x plus y. And so n divides this thing here. And in here, we have to find out if, say, what happens with x minus x squared plus y squared. So we have two cases. Let's perhaps do it here. If x is congruent to y modulo 2, then it means that x squared plus y squared is even. Either they are both even or both odd. So in this case, I'm sorry. We have already shown that n divides the whole thing because n divides the first parenthesis. And then we have to show that we can divide by 2. So that we have to show that this is an even number. If x is congruent to y, then x squared minus y squared is even. And if x is not congruent to y, modulo 2, then x squared plus y squared is odd, and 1 plus x squared plus y squared is again even. So in all cases, the first or the second part are even, which means that we can divide by 2. And so n divides really the whole part here. And so it shows that this is a compatible function, which is not a polynomial function. Okay, so these things really can happen. Then we have question 16. Oh yes, I know that some we have some more visitors. So here, so the remaining lectures are December 14 in 1 week, and then 3 lectures in January on the 11th, 18th, and 25th for 25th. So question 16 asks the following question. If a ring R in the variety of commutative rings with identity, if this is polynomially complete, then we want to show that it's a finite field, but that's easy. If it's polynomially complete, we know that it's simple. And a ring which is a commutative ring with identity, which is simple, is a field. And we have seen last time that the finite fields are polynomially complete because you can interpolate at every place, and there are only finitely many by Lagrange polynomial interpolation formula. And if R is an infinite field, it cannot be polynomially complete. So we see that R is even a finite field. So the only polynomially complete commutative rings with identity are precisely the finite fields. And we have a third question. It asks for the number of polynomial functions on Z modulo 4. Well, it's not quite easy if you don't have a formula to find out all functions from Z4 to Z4, which are polynomial functions, because without any theory, you have to take all 4 to the 4. It's 16 squared, so 256 functions. And for each, you have to decide if it's a polynomial function or not, which sometimes is not quite easy. But fortunately, we do have a formula. This is given in this case by 2 to the power of 2 times n plus 1 minus s. And in here the meaning of n is the largest integer. Such that n, which n smaller capital, that the order here 4 does not divide, the 4 does not divide n factorials. And you see from that means that n, capital N must be 3. 4 factorials already divided by 4, so n is equal to 3. And what is s? S is the power of 2 in the product of I factorials, I going from 2 to the order of the group minus 1, so it's from 2 to 3. Yes. And that's 2 factorials times 3 factorials, which is 2 times 6, which is 12. And 12 is 2 to the second power times 3 to the first power. And this exponent here is just equal to s. A very strange formula, so that this will give you the number of polynomial functions. And if you plug in these values, then you get as a result 2 times n plus 1, that's 2 times 4 is 8, minus 3 is 2. So it's 2 to the 6, which is 64. And how much is this 64? Well, we have altogether 4 to the 4 functions from Z to Z. So it's 265, and this is just 1/4 of the number of all polynomials. So this is just 1/4 times the cardinality of m of Z4. So the part of all functions which are polynomial functions is just 1/4. 1/4 of all functions fulfill this. Yeah, let me add, because this formula was just for powers of a prime p, but as a remark, the number of polynomial functions over set p to the n times set q to the m. That's just the product of number of polynomial functions over set p to the n times the number of polynomial functions on set q to the m if p is unequal to q. So the number of polynomial functions, that's multiplicative. If you have different prime powers, you simply have to multiply them, which means that for any n, you can now find the number of polynomial functions over set n, simply decompose n into the product of prime numbers, and do this formula for every prime number which divides n. Yeah, are there any questions concerning that? Okay, so we will continue with this. Let's start. What was the reason of that? Well, last weekend we had a type of holiday. We remembered Saint Nicholas. He was a bishop many, many centuries ago, and he did good things to poor people and especially to children. And so he is now remembered in this way, that a bishop is dressed up on these days and goes from door to door, from families to families, giving goodies to, especially to children who have been good throughout the year. However, when there's something good, there's always also something bad. It's like a yin and yang, and so together with the bishop, there comes also the devil, and the devil comes to children who are not so good, and they will not get any goodies, but they will get some slight punishment. Well, for years or decades, only the devil came to my house, and so I only know this very well, and I wanted to show this part of Austrian tradition to you as well. Before we really continue, I must apologize. Last time I was a bit too fast or too sloppy in an argument of a proof, and so I would like to correct it. That's the proof that if A is an algebra in a variety of expanded groups, and a small a, an element of this, we might ask how the ideal generated by A looks like. And the thing was that the principal ideal generated by A is given by the set of all P bar sub A of A, where P is a zero-symmetric polynomial in a V of X. And let's put down the zero-symmetric part in here. And this complicated thing will have abbreviated by A in brackets. And in the proof, it didn't really come out why this polynomial or polynomial function have to be zero-symmetric. The first part was okay. We showed the first part that A in brackets is an ideal. And we did correctly until we got a normal subgroup. The only thing was to show that the ideal property holds. The ideal property in expanded groups is the following. So to show that whenever you have some n-ary operation of, say, p1 plus p1 of A up to pn plus pn of A minus the operation of the elements of p1 up to p sub n, where the p sub i's are in A, and the p sub i's are zero-symmetric, that this will again give us an element of A in brackets. But what we see here, this thing can be easily rewritten in the following form. That's the composition of P1 plus P1 up to Pn plus Pn minus the composition of P1 up to Pn. Well, I identify here the constants P1 with the constant polynomial P1 and so on. And we let everything here act on A. So that's the same as above here. And what we have here in this bracket is a polynomial, of course. And this is a zero-symmetric polynomial, but because what happens if you insert 0, 0 here, then you get the composition of P1 plus P1 of 0, which is 0 because P1 is zero-symmetric, and the same with here. So you get the composition of P1 up to Pn minus the composition of P1 up to Pn, and so this is even. This is 0, so it's a zero-symmetric polynomial, and this shows that the whole thing here is back into A in brackets. Now, what have we seen up to now? We've seen the following, that A in brackets is an ideal. It contains A. And this ideal in parentheses here is the smallest ideal which contains A. So we have the information that the ideal generated by A is contained in A brackets. Okay, at least one part. The second part, we have to show that the converse is true. And for the having the converse, I found another proof which is more transparent, perhaps, and I also think more elegant. We have to take an element in here. So we take some p bar of A. Yeah, I omitted the capital A up down here. Take p bar of A in capital in A in brackets. We know p is a polynomial function. P bar is a polynomial function. So that's we have that had that last time. So it's also a compatible function. So p bar is compatible. Now A is certainly equivalent to 0 concerning the principal ideal A, because A is in the principal ideal generated by A, so it's congruent to 0, which means that p bar of A is equivalent to, with respect to the ideal A, to p bar of 0. And again, you see here we need zero-symmetric. The P is zero-symmetric, so this is 0. And this shows p bar of A is equivalent to 0, which means p bar of A is back in the ideal generated by A. And now we have both proven both sides. So the ideal generated by A is really the same as the set of all polynomial values on A, of all polynomial values which are zero-symmetric. So this gives, I think, a fairly nice description of all polynomial, of all generated ideals in varieties, in all varieties of expanded groups. Yeah, and now we finally can continue our considerations. We were in the chapter on, or in the section on equations, and so we continue on equations, and we'd like to find out if some equation, remember an equation is just a single polynomial, and we think in the back of our head that this means the polynomial equation p equal to 0, or to find values so that p of A, p bar of A is equal to 0. If we can find some solutions either in the algebra A or in some extension of A. As I mentioned last time, this seems pretty hopeless to find this, and maybe we can get some information which says there exists some extension or something like that, but we can even tell in which extension this equation will have a solution or not. That's a rather, I think, sensational. And first of all, let's start with some little proposition. same setup as we had last time, then we can say a solution of the equation P, where P is a polynomial over A in a variety V of X. A solution of this is also a solution of all polynomials which are in the ideal generated by P. So this is also a solution of all Q, where Q is in the principal ideal generated by P. You know this very well. If you have a polynomial P over the, say, over the reals, and if you have a solution, a zero of this polynomial, then it's also a zero of 2 times P, or of 10 times P, or of Q times P for any multiple. And this is the counterpart of this. We can do it here. So we can say that if we have a solution A, now may I give it here, solution A of this, A is a solution of all Z times P, of all, where this means P plus P plus P and so on, Z times, which is clear. And A is also a solution of all. And now we use the building construction for ideals of all, again, composition, an n-ary composition of say R1 plus I1 up to Rn plus In, where the I forgot, minus the composition of R1 up to Rn, where the Ri are elements in capital A, and the I, no, not Ri, are J, and the Ij are elements in the ideal generated by P. That's what we want to show. But this is very easy and trivial. Simply plug in A into the whole thing. You get the composition of R1 of A. And if you compose it, take it at 0, you get R1, the composition of R1 of 0 plus I1 of 0. But that's in this ideal, and so it's 0. And now you know the trick which goes on. Rn of 0 minus, again, 0, the composition of R1 of 0 up to Rn of 0, which is 0. And so you see, whenever we build up elements of the ideal generated by A, we start with the basic things, and then that should perhaps be rewritten as an induction proof, but I think it's trivial, then we always get zeros of these new polynomials here, which are in the ideal generated by P. And we can be fortunate to know how the ideal generated by P is. It's just another application of the result we had in the beginning, how generated ideals look like. So this means instead of saying a solution of a polynomial, we can simply speak of a solution of an ideal. Because whenever A is a zero of P, it's a zero of all polynomials in the ideal generated by P. Some of you might remind this to commutative algebra, where they also make use of this, but only in the case of commutative rings with identity. And so what we can do is to say, to speak of a zero of an ideal. Okay, that's needed later. And now the real surprising theory says the following. And this is called Hilbert's weak Nullstellensatz. And Hilbert's weak Nullstellensatz says that whenever you have a polynomial P, then we can, so if P is in AV of X, then the equation P is solvable over A. So it means that it's solvable in some extension of A, some extension B of A, which still has to lie in the same variety as we started with. This is true if and only if the ideal generated by P does not contain any constants. So the intersection with a V of X, and here the constant part is equal to 0. So that's the main thing here. An equation is solvable if the generated ideal generated by P does not contain any constants. But in one way, it is clear, because suppose there would be a constant in here. We know every a constant in this ideal, so it must be a solution of this. And the constant, if we write it in ordinary language, it means the constant in here would be equal to 0. You cannot have this. The constant can never be 0 unless it's 0 itself. And this condition is also is sufficient and necessary for the existence of an extension of A in which the P has a solution. And I simply indicate the proof in such a way. So we have this. If C is a constant in P, then we have the equation C is equal to 0, so C must be 0. That's the easy part. The other one, suppose this condition is satisfied, then we can say we find an extension, and this extension can even be simply indicated. The extension B can be simplified in such a way that we take the polynomial algebra AV of x factored out by P, the ideal generated by P. This is still in the variety V. And in there, P has a solution, namely P itself, because P will be moved into the ideal generated by P, which is the 0 in this factor. And so in there, P has a solution which is equal to P, and you will find this in some way unfair, but you know this idea already from field theory, when one proves that every irreducible polynomial has a 0 in some extension. So that's the same atmosphere as we have here. So by Kroneker's theorem, we have the same thing. We take, if we want to find a 0 of a polynomial, we take the polynomial algebra, factor out the ideal generated by P, and in there, P itself is trivially a solution of this. So the ideals are pretty similar to field theory, but they really work over any variety of expanded groups. The main idea why we need this here, that didn't come out, that would only come out if I really do the proof in detail, but I don't want to do this because the main thing is that we get B as an extension of A. So A should be contained in B. And if P does contain constants, then also here in A, some constants would be identified in the factor. And so this would not be an extension of A anymore. That's the main thing why we need this condition here, that the only constant in the polynomial generated by P is 0. Now that's good news, and let's try to use this in such a way that we take some equations which we have done so far, and to find out if they will have a solution in some extension or not. And this really is a wonderful result, and much more than you could expect. You know that if this condition holds here, you can decide this in A or in AV of x. You don't have to go to some big extension. And then it says you will find some extension, and it also gives this extension here explicitly, where you have a solution, and it gives the solution explicitly. What else can you ask for anymore? So let's try to test what we have gotten so far. And we take as a first example x squared plus 1 over the real numbers. And we are working in the variety of commutative rings with identity. We know that there exists an extension, C, complex numbers, where this has a solution, but we don't have to know this. We simply have to find some ideal, or to ask, is there a constant unequal to 0 in the ideal generated by x squared plus 1. But how do the elements look like here? They are just multiples of x squared plus 1. So that's given by all q times x squared plus 1, where q is in r of x. And it's clear, no extension of this, no multiple of x squared plus 1 can be some constant. So the answer here is no, which means there exists an extension, and if you work out the thing a b equal to a v of x factored by p, as you perhaps know from elementary ring and field theory, this extension is just isomorphic to the complex numbers. Take all polynomials factored out by x squared plus 1. That means you replace x squared by minus 1 at every time, and in there this will have a solution. Another example. What happens again in the variety of commutative rings with identity? What happens with the polynomial or the equation 2x plus 1? And we take this as an element of set 4 of x. And we can ask again, is there a constant unequal to 0 in the ideal generated by 2x plus 1? And in fact, we simply can take the square of this. So the answer is yes. Take 2x plus 1 squared. That's in this ideal here. And this is just usually would be 4x squared plus 4x plus 1, which is equal to 1, since we are over the integers modulo 4. And so we get a constant, namely 1, in this ideal. And this means that there is no extension of the integers modulo 4 where this equation will have a solution. Oh, that's really something. And so that's great. And last time we worked quite hard to find if the same equation 2x plus 1 is solvable over z times z2. We found out that it's not, but now we can solve this question much easier. And this is question number 19, I believe. Yeah. sure that the equation x squared plus 1, no, 2 times s, 2 times x plus 1 is not solvable over z times z2. It's quite a good exercise to do this, really to find out what's the point where you get, or how to you get a constant in the ideal generated by 2x plus 1. Yeah, so far we have spoken about single equations, but we can do the same thing with not only single equations, but with collections, with systems of equations. And this is just then a set of polynomials, and we would like to find a common solution of all of them. So another topic would be systems of equations. So it would be P1, P2, and so on. And the thing is the same. We look for solutions of P1, P2, and if we find a common solution, then we have a solution of the whole system of equations. So it doesn't bring anything new, and there exists a version of Hilbert's weak Nullstellensatz also for systems of equations. Another topic would be to count the number of solutions. You know, this is a famous task in elementary mathematics. Excuse me? Okay, can't hear you anymore, sorry. The number of solutions, if you have a polynomial over, say, over field of degrees 8, then you know the number of solutions in this algebra is at most 8. But if you have polynomials in other classes, then it can be completely different. And Karl Maxen, Peter Fuchs, and myself found the following, that the following result: if you take a skew field, and if you take a P out of S of X, where this is a skew field, then P, the equation P, has finitely many solutions. If and only if S is a field. That means as soon as you go away from fields, from commutative fields to skew fields, you can always find infinitely many solutions for polynomials, and I have to say of degree at least 2. For instance, take the quaternions, the two-dimensional extension of the complex numbers, then we take again the polynomial x squared plus 1. And this has solutions. We know over the complex numbers, it has plus minus I, the root of minus 1. But now it has many more solutions, namely all of them of the type cosine of alpha times I plus sine of alpha times j, where I, j, k are the roots of minus 1, so to speak, and alpha is any angle or any real number. So you simply multiply it out and you get infinitely many solutions. In fact, denumerably many, countably many solutions of this equation of degree 2. So it's quite interesting that the nice thing, a polynomial of degree 20 has at most 20 roots. If you go to skew fields, this is not true anymore. You always find infinitely many solutions. So there are some other pretty interesting topics in the area of polynomials, and I'd like to at least to mention some of them. Some more topics. The first would be perhaps to ask this. We had a connection between polynomials and polynomial maps by the map H, which was from A of x to P of A by taking each polynomial P to the corresponding polynomial function. You know this. And we know that this is a homomorphism, in fact, an epimorphism, but we don't know if it's an isomorphism or not, except in some special cases. You know, we even don't know it for commutative rings with identity when exactly H is a isomorphism. And so if we don't know it, we are interested in the kernel of H. So if we have the kernel of H, that consists of polynomials such that the corresponding polynomial function is the zero function. And so that's the reason why if we take a polynomial P in here, we call P a vanishing polynomial. Because when we take it as a polynomial function, it vanishes at all places. Can we find out this? Well, if we know something about the kernel here, then it might be very, and it is very helpful in counting polynomial functions. Counting polynomial functions is not easy. You see, even in the case as we had set sub 4, the formulas are quite complicated already. So, for instance, over the Calar field of order q, the polynomial x to the q minus x is vanishing. because over this field, every element, they are just characterized by that, is a root of this polynomial. So this polynomial is, the corresponding polynomial function is always 0. Maybe an example over a group G. So, suppose G is a group of exponent 3. Then, of course, 3 times x is vanishing, because it means 3 times every element is equal to 0. So we find some example here. Now, one knows quite a bit of vanishing polynomials over fields altogether, not only over finite fields, but it's sometimes, the things get pretty much involved. What about vanishing polynomials over groups? This can be rephrased in this way. The polynomial functions on G are just the sums of or differences of inner automorphisms plus a constant. And so the question arises, when is take away the constant, when is the sum or difference of inner automorphisms vanishing all the time? When is it 0 all the time? And in order to find out something about that, I organized a meeting, or 2 meetings in 2009 and 2010, and there were the main actors there were Gary Peterson, then Stuart Scott, and Erhard Eichinger. They described polynomials P, or say P is vanishing on a group G if and only if, and so on. Or but another one was John Meldrum. They came to Linz in 2009 and 2010 for about 6 weeks, and we worked hard on this solution here. And they really found a solution. It's quite complicated, but there are now, I think, 8 or 10 papers, deep papers written on this topic. And in order to describe this, John Meldrum even had to invent a new type of product to describe this, and he called this the Linz wreath product because he found it in Linz. So that was a good success story to find all the elements, all the polynomial which are vanishing on a given group G. Yeah, another collection of 2 topics are the following. If you think back to the polynomials over the reals, then you know that if you take the polynomial x to the third, it has the shape, and so it's bijective, which might lead us to the to ask a question: for which polynomials p is the corresponding polynomial function bijective? So a polynomial p in the usual thing, uh, such that p bar is bijective. Bijective functions from a set into its set are often called permutations, and so we call p a permutation polynomial. Um, if a non-wave p bar is bijective. So we have already mentioned one, x to the third is a permutation polynomial over the reals. And there are many more over the reals. But in order to characterize them, how they look like for general rings is pretty difficult. There exist a lot of things, a lot of papers about this. And the big names there are Rudy Liedl, Gary Mullen, and the Pilz. These are the, well, among the famous names in permutation polynomials, and this has developed into a research area in its own, and so it has a lot of results. Some of them are pretty complicated, and I don't want to go too far into detail for that. But the nice thing is that Liedl and Mullen found out that these permutation polynomials have interesting applications, namely to RSA crypto systems. That's in order to permute the encoded elements further and so on. Three. Another interesting topic is the following. You take polynomials, say, over the, again, variety of commutative things with identity, and you take all polynomials and now you take a field F of characteristic P, so particularly a finite field, but can be infinite as well. And if you look at all polynomials, now we have 2p, polynomial and prime. So let's take all q composed with x to the p. Now q is in f of x. That's a quite interesting thing. How do they look like? Well, these are all polynomials of the form a sub naught plus a sub 1 x to the p plus a2 x to the 2 times p and so on. And these polynomials are quite famous in field theory because they are called linearized polynomials. But you see, they are by no means linear. So by this name, and this name is quite interesting and good because these polynomials have the property that they are distributive. And in fact, these polynomials here, they form a subfield of the polynomial ring f of x, polynomial nearing f of x plus composition. That's quite interesting. The polynomials do form a nearing, and within this nearing, we have a subnearing, which actually is a field. Well, we have one subnearing, the constants. They form a field. That's not interesting. But these polynomials here have the property that they are distributive. What's the reason? If you take x to the p and composed with a sum of two things, then the binomial theorem tells us it's so x to the p composed with, say, f plus g. That's equal to f of p plus g of p plus some other elements in between, and all of them in between have p as a factor, and hence, since we're in characteristic p, all of them will vanish, and so we get this, and this can be again written as x to the p composed with f plus x to the p composed with g. And so x to the p and the powers of this, they are distributive elements, which means that within the nearing you find distributive polynomials with respect to composition quite unexpectedly, and they have a nice number of other algebraic properties, so they are interesting for field theory. So, more topics. If you want to find applications to fields of these polynomials, look at the famous book of Liedl and Niederreiter. On finite fields. That's still the Bible of this subject of finite fields. Another interesting thing, this would be topic number 4, would be what if we take polynomials in one of the earlier versions as sequences. We had polynomials over the commutative rings with identity as sequences which after a certain point continue only with 0, 0, 0. But what happens if we don't stop? Then we get infinite sequences, and what we get if you start with a ring, a commutative ring with identity, we can take R of x as the set of all a0 plus a1x plus a squared, a2x squared, plus and so on, where the a sub I and r, which do not necessarily stop. And this is just another way to write the sequence a0, a1, a2, and so on. And these are called formal power series. Formal because they look like power series, but you don't have to care about any type of convergence, because convergence is not a topic in here. That's not really a sum. it's just another way to write this, a more intuitive way to write this. And for these sequences, we also don't think of or consider the question if they, as a sum, converge in some way. Now, R of X is again a commutative ring with identity, and we can also do the following, that we take the composition into account. So we also can take a composition a sub naught plus a sub 1x plus and so on, composition with b naught plus b1x, and do the composition as usual, as one does it with polynomials. But now there is a very unexpected obstacle in order to do this. What happens with the result here? Well, we can order it in such a way that we have a sub naught times b sub naught and then later on we have a sub naught times b1 times x, this way, plus a sub 1 times b naught times x, and so on. And if you do this for a while, you see that you will never get rid of b naught here. So in this case, you get you would get infinite sums also in this way of writing it as sequences. And infinite sums are not a topic of algebra. So this is not defined. And so you have to restrict it to the case that you have no constants here. And you get the formal power series R naught of x with plus and composition as a near-ring. There exist some extensions. Sometimes it suffices to say the constant element had to be nilpotent. Every other element can be as it is, and this still makes up a near-ring. But these near-rings of formal power series prove to be interesting in some other area, and maybe we'll have time to look at the combinatorial applications of this. So by now you might have asked why I am telling so much and so long about polynomials and polynomial functions. And one of the reasons is, as I mentioned last time, polynomials and polynomial functions are nonlinear, but in a way which can still be handled. So it's a tame type of linearity. Another thing is that we have a result of the following form. It goes back to John Meldrum, Yang-Xian Zhou, and myself. And it says, for every near-ring n, there exists a variety of extended groups in an algebra A in this variety such that n can be embedded into AV of x. So it says the polynomial algebras or polynomial nearings are again Catholic examples in the class of nearings. You can represent every nearing not only by mappings uh, as we have seen, but also by polynomials. And this is quite nice because it says AV of x do play a universal role in the theory of nearings. But that should end up our trip to polynomials and polynomial functions. And yeah, maybe there are a few more minutes to go. So let's start with chapter number 7. And now we go to planar nearings. That's the area where I think are the most convincing applications for practical purposes of nearings. So these are planar nearings. But first we go again back to equations, which we have discussed last time and this time, and to geometry, where we had usually have the requirement that two lines should have one point of intersection. Now, suppose we take a nearing now. And we look at the equations. We want to have lines represented by linear equations of the type, say, a1x plus b1. And if we have another line, y equal to a2x plus b2, then we usually would like to have a point of intersection, a unique point of intersection, unless they are parallel, so unless a1 is not the same as a2. Well, let's simply try if that works in the nearing, and we can find out what it is. We simply take a1x plus b1 equal to a2x plus b2, like in good old childhood, where we had to do this over and over again. And now we simply take it on the other side. We have a1x minus a2x is equal to b2 minus b1. And now we have just the right, the suitable distributive law at hand to write this as a1 minus a2 times x is b2 minus b1. And that's about the point where we can stop. We can say this equation has a unique solution here if this element a1 minus a2 is invertible. Or we can say it always has a unique solution with b1 and b2 here. So it has a unique solution if a1 minus a2 is invertible. Well, but that means we don't have a very interesting situation. We simply have to check if a1 minus a2 is invertible in the nearing or not. So there's not much to do. Well, still, we have to say what we need for invertible is a unit element. And so in this case, if we have a unit element, then we are done. Now let's make things again with a slight change here. Let's now take the lines as y equal to xa1 plus b1 and y equal to xa2 plus b2. You might say, well, that's a simple, useless change of order here, but it's not. We can do this same thing here until here, but in here we see that we get xa1 minus xa2 is b2 minus b1, and now we are it's hopeless because we don't have the suitable distributive law to take x out, and we simply say we have to stop here because we cannot do anything else. So what it amounts to is that we might take the xa2 again on the other side or so, and what it amounts to is to look at equations of the following type. We ask when does every equation of the type xa is equal to xb plus c, I changed the notation a little bit, have a unique solution. Well, there might be some near-rings where this is true, some near-rings where this is not true, and we would like to classify those, and we have no idea at the moment how many applications will be ahead of us. Just in the change from this uninteresting situation to this interesting situation, and we call near-rings which have this property planar near-rings, and we'll continue with planar near-rings next time. So time is over. Have a good rest of the week, and I hope to see you again next Monday for the last lecture before Christmas. Bye-bye.
Thank you. Thank you.
Bye.
Bye-bye.
Goodbye.
Bye-bye. Yeah, since I see Bernd Henschenmacher, Bernd Henschenmacher will give us an account on applications of distributive or non-distributive systems in physics next time. So I'm very much looking forward to have you here next time as a part-time speaker.
Thank you very much. It will be an historical account, but unfortunately there are no real applications so far for near-rings in physics, but I will give an account on early ideas, how to apply near fields and near-rings to physics. So maybe it's of interest, but yeah.
Will be interesting. Great.
On next Monday.
So see you all next week. Bye-bye.
Bye.
Kann ich da noch mal